Most stereochemistry labeling mistakes occur when students confuse describing one single molecule versus comparing two molecules. This video draws that line clearly. We are only describing single molecules. Hey there, ninjas. In this video, we're going to describe a single molecule. We are not comparing the relationship between two molecules. We are describing the state of a single molecule. The only question we care about for this video, what kind of molecule is this? You see, words like enantiomer and diastereomer describe the relationship between two molecules, and we'll talk about those in a separate video. This video refers to words that describe a single molecule itself: chiral, achiral, and meso. If you mix those two categories, the descriptor words and the relationship words, that's when stereochemistry gets all jumbled. A molecule is chiral if it is not superimposable on its mirror image. The opposite of chiral is achiral, not chiral. An achiral molecule is, yes, superimposable on its mirror image. This isn't about wedges or labels, it's about whether you can take one molecule and rotate it and manipulate it to sit perfectly on top of another molecule. Let's start with these two examples. First, let's look at how many stereocenters there are in each example. The first molecule has 0 stereocenters. The methyl group has 3 identical hydrogens. The central carbon has 2 identical methyl groups, and carbon number 3 also has 3 identical hydrogens. The second molecule has 1 stereocenter. The central carbon is attached to the methyl group, the chlorine, the bromine, and the implied hydrogen. This carbon is a stereocenter. How do we know if these molecules will be chiral or achiral? Let's go through the whole analysis, and then I'll show you some shortcuts. We start by drawing one of the 3-dimensional representations of this molecule. We'll put the chlorine on a wedge. Then we need to draw the mirror image. If I were to number these carbons 1 through 3, reflecting this molecule through a mirror would put carbon number 3 on the left and carbon number 1 on the right. If I were to reflect this molecule through a mirror, the chlorine would still be on a wedge. You probably won't be able to have a phone on an exam, but while you're practicing, if you hold your phone up to one molecule, you can see the mirror image reflected in the screen. And what I want to ask is, are these two molecules superimposable? Can I pick one up, rotate it, manipulate it such that it sits exactly on top of the other one? And what I want you to see is that yes, these are identical molecules. Even though it's a mirror image, if I were to pick this mirror image up and just translate it and put it right on top of the original, these are the same molecule. So when the molecule, yes, is superimposable on its mirror image, this molecule is achiral. Let's do the same analysis for the molecule with 1 stereocenter. I'll start by drawing one of the 3-dimensional arrangements of this molecule with the chlorine on a wedge. To draw this molecule's mirror image, I'll reflect it through a mirror that puts the bromine on the left and the carbon on the right, and it keeps the chlorine on a wedge as we reflect it through a mirror. And the question is, are these two molecules superimposable? Can I pick one up, rotate it, manipulate it to sit it exactly on top of the other one? Well, let's take a look. I see that the chlorines are both on wedges, so they look like they're superimposable, but in one, the bromine's on the right, and the other, the bromine's on the left. Let's do a pancake flip of this molecule to see if we can get the bromines on the same side. If I take this molecule and rotate it like a pancake, that's going to put the bromine on the right side of the molecule. But it's going to take that wedge group and shift it onto a dash. We solved one of our problems. We got the carbon and bromine to be superimposable, but now the chlorines are not superimposable. In fact, no matter how I try and rotate or flip or manipulate one of these molecules, I'll never be able to get them to be superimposable. So a molecule with 1 stereocenter is, yes, chiral. And these are 2 fast rules that are always safe. Any molecule with 0 stereocenters will always be achiral. We will always be able to take, rotate, manipulate, and flip the mirror image to be identical to the original. Likewise, any molecule with exactly 1 stereocenter will always be chiral. We'll never be able to take the mirror image and rotate, flip it to be exactly the same as the original. So what about a molecule like this? A molecule that has 2 stereocenters. Will a molecule with 2 stereocenters be chiral or achiral? The answer is, it depends. And this is where students can get burned. A molecule can have 2 or more perfectly good stereocenters and still be achiral. How can that be? Symmetry. If a molecule has an internal plane of symmetry or can be rotated into having a plane of symmetry, then that molecule is achiral. If there's a plane of symmetry, the molecule can be superimposed on its mirror image, and that makes it achiral, even though it has stereocenters. This molecule is structurally symmetric. It's palindromic. A palindromic molecule is a molecule that reads the same left to right, just like a palindromic word, like mom, M-O-M in both directions, or noon. Because this molecule is palindromic, that means that it might be achiral. We'll start by drawing one version of this molecule with both of the stereocenters on wedges. As I go to draw the mirror image of this molecule, notice that the last bond goes up and to the right. So when I draw the mirror image, the bond is going to start at the top and go down to the right. If I add carbon numbers to this molecule, carbon number 4 will be on the left and it will go down to carbon number 3 in a good, perfect mirror image. Then I can continue up to carbon 2 and back down to carbon 1. For the chlorines, in a mirror, the chlorines are going to stay on the wedge in the mirror image. So the question is, are these superimposable? It might not be as straightforward as you think right away. I can't just translate this molecule over because they're not oriented the same. On the left side, the bond goes up, and on the left side of the mirror image, the bond goes down. If I were to translate these over, these bonds would be going in opposite directions. In order to check if they're superimposable, the carbon backbone needs to be drawn in exactly the same left to right orientation, and right now they're not. I can manipulate this mirror image to make it in the same orientation as the original by taking this molecule and doing a vertical pancake flip in order to get the left-right orientation the same. If I flip this molecule vertically like a pancake, the carbon on the left goes down and then up to the next carbon. That puts the carbon chain in the correct orientation. And when I do a vertical pancake flip of this molecule, the chlorine group that was on a wedge will now be oriented on a dash. And we see the issue. If I can get the carbon chain to be oriented in the same left to right, now the wedges and dashes are opposite. If I can keep the chlorines on the same wedge or dash, now the carbon chains are in the wrong orientation. This is actually quite common. For molecules with more than one stereocenter, most of the time they will, yes, be chiral molecules. Especially for molecules that are not palindromic, that are not structurally symmetric. Any molecule that's not structurally symmetric with 2 or more stereocenters will, yes, be chiral. It's only when a molecule is structurally symmetric that we need to be extra careful. Let's look at the same structural skeleton, but with the wedge dash version of the stereocenter. If I want to draw the mirror image of this molecule, I can give this molecule some carbon numbers. The mirror image is going to start with carbon 4 on the left, going down to carbon 3, up to carbon 2, and back down to carbon 1. As I reflect this through a mirror, the dashed chlorine on carbon number 3 will still be on a dash, and the wedged chlorine on carbon number 2 will still be on a wedge. Like we've seen before, this looks like it should not be superimposable. If I pick this molecule up and place it on top, the carbon chain is in the wrong orientation. In this molecule, the first bond is going up to the right, and in the second molecule, it's going down to the right. In order to fix that, I can do a vertical pancake flip of this molecule to see if I can get the carbon chain in the right orientation. If I do a vertical pancake flip of the mirror image, now the first bond goes up to the right, down to the next carbon, and up to the last carbon. As I do a vertical pancake flip, this chlorine that's on a dash will now be flipped up into a wedge. And this chlorine that's on a wedge will now be flipped down onto a dash. And look what just happened. Now these two molecules are the same. They are superimposable. I can pick up the orange one and put it directly on top of the green one. They're the same molecule. So unlike we've seen before, the mirror image is not a different molecule. The mirror image is the same molecule drawn twice. This is a molecule that had 2 stereocenters, but the wedge dash version and its mirror image are, yes, superimposable on each other. This molecule is achiral due to an internal plane of symmetry. That makes this one molecule drawn several times meso. Meso is a descriptor word that describes a single molecule where the molecule has 2 or more stereocenters but is achiral because its mirror image is superimposable. Meso is not a relationship word between 2 molecules because I don't have 2 different molecules. I have the same one molecule drawn several times. Recall, this is a video about descriptor words. Meso describes a single molecule. Our textbook definition of a meso molecule is a molecule that contains 2 or more stereocenters and contains a mirror plane or can be rotated into having a mirror plane. As drawn right now, though, none of these molecules have a mirror plane of symmetry. So let me prove that to you. Let's look at these molecules again. The first is the wedge-wedge version, the molecule that we said was chiral. And the second is the wedge-dash version, the version that ended up being meso and achiral. If I take this original molecule, I can rotate around the central carbon-carbon bond by doing a 180-degree bond rotation. Being able to rotate, flip, and manipulate molecules has been very important in this entire exercise. If you don't feel confident with that skill, I have an entire series of videos that I'll link to in the description below that shows you how to rotate, flip, and manipulate molecules. If I do the 180-degree bond rotation around this molecule, something very interesting happens. After rotation, the molecule now has a central mirror symmetry plane. The one half of the molecule is directly symmetric to the other half of the molecule. Let's rotate each of these 180 degrees around their central carbon-carbon bond, and let's see what happens. For both molecules, as I do that, the chlorine on the left stays on the wedge. For the molecule at top, when I do this rotation, the chlorine that was on a wedge after 180-degree rotation will end up as a chlorine on a dash. For the bottom molecule, when I do that 180-degree rotation, the chlorine that was on a dash will now be rotated up onto a wedge. And notice what happened with our bottom example. Now we have a perfectly symmetric molecule with a plane of symmetry right down the middle. The wedge chlorine on the one side is perfectly symmetric with the wedge chlorine on the other side. That's not true with our top example. the left side is not perfectly symmetric with the right side, the wedge and the dash is opposite. It is in this rotation that we can see the full definition of meso, a molecule with 2 or more stereocenters that has a mirror plane or can be rotated into having a mirror plane. Whichever method you use, trying to find the mirror plane or drawing the mirror image and trying to manipulate it back to the original, make sure you can find chiral versus meso molecules when the original molecule is structurally symmetric. These same patterns hold for molecules with 3 or more stereocenters. With 3 or more stereocenters, if the molecule is not palindromic, if it is not structurally symmetric, a molecule with 3 or more stereocenters will, yes, be chiral. However, if the molecule is structurally symmetric, if it is palindromic, then we have to be very careful because some of those versions of the molecule may be meso. If this video felt slower than normal, that was intentional. Meso is probably the most confused term in the entire stereochemistry unit. The biggest misuse of the word meso that I see is when students try and use meso to describe the relationship between 2 molecules. The relationship between these 2 molecules isn't meso. Meso is a descriptor word. This one molecule, drawn twice, it is meso. Once you can cleanly separate descriptor words, then you're ready to move on to relationship words between 2 molecules. And separating out those 2 categories makes stereochemistry much more manageable. No more guesswork. You're building the right way.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.